Hey guys, this is Tiffany Zong from Physics 2211, section M6, and today I'll be narrating Lab 1, Constant Velocity. The purpose of this procedure was to explore the principles of motion as they pertain to an object moving at a constant velocity. Based on Newton's second law, we know that force is equal to mass times acceleration. This means that as long as a net force is acting on an object, it will be accelerating. Since an accelerating object is changing in either speed or direction, in order for an object to be moving at constant velocity, it must not be accelerating. Thus, an object moving at constant velocity necessarily has no net force acting on it. In reality, it's rare to find an object moving at perfectly constant velocity because forces such as friction, air resistance, and gravity are constantly acting on objects in motion. However, it is important to note that an object can have forces acting on it but still have a net force of zero, so long as the components making up the forces cancel out. For the purpose of this experiment, we approximated constant velocity by rolling a pencil in a straight line across a flat surface, a desk. The footage of the pencil rolling across the desk was recorded with a smartphone camera and then later opened in the video analysis program Tracker for examination. In Tracker, we set the origin of the position to the left of the pencil's initial position and defined movement to the right as the positive x direction. The part of the video analyzed starts right at the point the pencil is released into motion until 1.47 seconds, or about 150 frames later. Using Tracker, we recorded data on the x position of the pencil in every frame of its movement. Then this data of position versus time was exported to Excel and graphed to find the approximate velocity of the pencil over the interval. After that, we used the knowledge of the pencil's approximate velocity in order to create a programmatical model of the pencil's motion in VPython. The idea behind using this model is to try to create data on motion which resembles our real-world scenario of the rolling pencil using our mathematical understanding of the principles of physics. As mentioned before, because the pencil moves at approximately constant velocity from our model, we set the net force to zero. In addition to that, the length of the steps of time for the modeling of motion, delta t, is set to about 1/30th of a second in order to approximate the lengths of the frames in the original video so that the data in the model may better match up to the video. Running our model, we see that it shows a blue sphere representing the pencil moving in the right direction, which we have defined to be the positive x direction. Then, having set the program to output the data for position versus time in a spreadsheet, we import the data into Excel to be graphed alongside our original data for the purpose of comparison. In this graph, the blue line represents the position versus time of the pencil in the original video we shot. The red line represents the position versus time of our VPython model. Notably, while our programmatical model of the pencil's motion approximately follows the original motion of the pencil, the graph of the motion of the pencil is slightly curved. We can attribute the slight curvature in this graph to the fact that the original pencil was not moving at perfectly constant velocity. The forces of friction of the desk and air resistance acted on the pencil to slow down its motion slightly as it rolled. In future labs, we may attempt to explore and model the effect of such forces on an object in motion, but for now we'll accept constant velocity as a reasonable model of the movement of the pencil across the desk for a short span of time. Finally, we'll explore some of the assumptions behind our model. For example, if we set the left direction to be the positive x direction, then we would find the pencil to be moving at negative velocity. Or if we define the origin to be the final position of the pencil rather than its initial position, we would see that the pencil is decreasing in position over time. The exploration of these what-ifs shows that a lot of how motion is modeled depends on the way we define the directions and positions. In a similar vein, if we had pushed the pencil at an angle, we could define the direction it was rolling in to be the positive x direction in order to simplify the modeling process. Perhaps in future labs, we'll continue to explore different kinds of motion. Until then, this is Tiffany Zong, and see you later in Physics 2211.